This program was sponsored by the Jesse and John Dance Fund. Since 1962, these lectures have been a forum for distinguished scholars of national and international reputation who have concerned themselves with the impact of science and philosophy on man's perception of a rational universe.
Good evening. My name is Marcia Andale, and on behalf of the Graduate School at the University of Washington, it's my pleasure to welcome you here to this evening's dance lecture. We're here tonight as beneficiaries of a generous gift from the estate of Jesse and John Dance. This lectureship and visiting professorship program was created in 1961 with a bequest from Mr. John Dance's estate. An additional gift was made by Mrs. John Dance in 1969. This bequest is intended to bring to the University of Washington and to the citizens of this region distinguished lecturers, scholars, and authorities of international reputation who, and I'm quoting from the bequest, who have concerned themselves with the impact of science and philosophy on man's perception of a rational universe. I think you will agree with me that this was indeed a far-sighted and invaluable gift to the university and to the citizens of this region. Tonight's presentation by Professor James Pebbles is one of over 80 presentations that have been supported by the dance lectureship. Before proceeding with tonight's program, I'd like to recognize a few individuals. Each year, we receive a large number of nominations for both the Jesse and John Dance and the Walker Ames professorships. From those many excellent nominations, we have to come to the tough decision of who to actually invite. And that tough decision falls to the selection committee. I'm not going to introduce all the members of that committee. What I would like to recognize the co-chairs, Dr. Michael Halloran from the Department of Classics and Dr. Gerald Baldesty from the School of Communications. In addition, the logistics of putting on an event such as this are no small matter, and all of those logistics are handled by a member of our staff, Mrs. Janet Jones, who's here with us tonight, and Janet has once again done a superb job of putting all of this together. Our speaker this evening is going to be introduced by a distinguished member of the University of Washington faculty, Professor Craig Hogan. Dr. Hogan is a native of Los Angeles. He attended Harvard University and earned his doctorate from King's College, University of Cambridge in England. Dr. Hogan held postdoctoral fellowships both at Caltech and at the University of Chicago. He worked on the faculty of the University of Arizona's Stewart Observatory and then joined our faculty in the Department of Astronomy in 1990. He currently is professor and chair of that department and also holds a professorship in the Department of Physics. It's my pleasure to introduce to you Dr. Craig Hogan.
Thank you, Marcia. Welcome, ladies and gentlemen. I'm very pleased so many of you could come tonight because I think we're in for a real treat. Our speaker, Jim Pebbles, is a great guy and a great scientist. He's a Canadian by birth and was educated at the University of Manitoba. And his academic career is very simple. He spent it since then at Princeton University, from graduate school ever since. His scientific career, however, is a much longer story, and since I know he's going to be too modest to describe his own contributions in detail, I just want to take a few minutes to outline the things that Jim's done for cosmology. Certainly when I was a graduate student a number of years ago already now, Jim was already recognized as the world leader in cosmology. In the early 60s, at Princeton, he was there when the microwave background was first discovered, the background radiation left over from the Big Bang. So that was the kickoff for the modern era of cosmology. Jim did some of the first calculations of the production of elements in the Big Bang. These are all things that he's going to tell you about in his lectures without telling you that he started the field. Production of elements and the microwave background are the two main reasons we believe there was a Big Bang. So he's the person to tell us about it. He's also pioneered many of the areas of the subject which are still unsettled, moving forward, and very active, such as the development of structure in the universe, the distribution of galaxies, large-scale structure, and the distribution of fluctuations in the microwave background on the largest scales, something which is, over the next few years, going to tell us perhaps a great deal about the very earliest stages of the Big Bang and the ultimate origins of all cosmic structure. So I'm really looking forward to tonight's lecture and also Thursday's lecture, which will tell you the answers to all the questions that he raises tonight. So I welcome Professor James Pebbles.
Thank you so much for those gracious words, Craig. We're old friends, but you laid it on. And it is indeed an honor and treat to be here. Today's lecture is going to attempt to convince you that we understand what the universe is doing in the large-scale average. A list, so as to speak, of things we think we know. On Thursday, I'm going to discuss some open research problems that we know we don't understand. Of course, the big excitement always is the things we don't know we don't understand. You hope that they will show up as we review such assigned problems as these mentioned here. There will be two themes running through these talks. The first, what grabs so many of us about the physical sciences, is the fact that apparently very different phenomena can be related by very simple rules that will in turn lead to the discovery of new phenomena. This fact that the physical world chooses to operate by rules that we can hope to deduce is a thread connecting particle physics, chemistry, geophysics, biophysics, and I'm going to try to convince you cosmology. Second theme, while we work on these problems of finding the rules that connect the phenomena of the physical world, we get to enjoy, at many occasions, images of the physical world that, for reasons I don't understand, tend to grab our imagination and attention. I offer you the example of this image of our planet Earth. I offer also evidence of how it moved people in the 1960s. Do you recall the Whole Earth catalog? An early version, only $1 then. Here, slightly later, in color, but for $3. This reflects a movement in society, you might remember, a great interest in active environmentalism, an attempt to bring our lives to a simpler form, more in tune with a sustainable nature and physical world. Many causes for that revolution in thinking, but I offer you here evidence that one of them was this image. It was no surprise, you understand. In fact, the ancient Greeks knew that the Earth is round. They could see the round shadow of the Earth cast on the moon during a lunar eclipse. During the centuries since the classical Greeks, people tended on occasion to forget this evidence, but by the time this photograph was taken, people knew, yes, the Earth's round, the oceans are blue, the clouds are white, and there are brownish, greenish continents. But yet, to see the image moved people and impressed them, showed them, here we are. We live on an island universe of very limited extent, and it would behoove us to take better care of it. Let me remind you that we live in a solar system orbiting a star, the sun. To set the scale takes light 8 minutes to travel. At least we should move these a bit apart. Is that okay? Yeah. From Earth to Sun. Major planet, Jupiter. And let me show you an image of Jupiter. What have I done? You're familiar with the fact that this is a gas sphere, has the same composition as the sun. It's not a star because it's not heavy enough to make the pressure at the center high enough to cause nuclear burning. It's still cooling off, though, from its original formation. That cooling off causes differential rotation, and the great red spot you can see in this image. Here it is blowing up from the early NASA flybys of Jupiter. The image is familiar to you if you watch the Weather Channel. It's a tropical storm. Of course, on a bigger scale, you could drop the Earth into this tropical storm. It's lasted for several hundred years, but the physics is the same as that of a tropical storm. The rotation of the planet with convection from below is causing this swirling eddy. Let's notice another planet, another beautiful image from the Voyager flyby. The planet, notice the wonderful rings that one now understands are small dust particles moving under the influence of several small moons, doing a very complicated gravitational dance to make these beautiful rings around Saturn. What we learned from so far, I think, is that the accepted laws of physics that account for example, a tropical storm, may be applied to a rather different situation, giving us qualitatively a very different effect, but yet it's the same old laws of physics that are uniting phenomena on very different scales. Now, we're not alone in our solar system. Here is, alas, a very poor copy of a beautiful model of the nearby stars. I at last was able to get a nice photograph of the constructor of this model showing the nearby stars, Professor Sarah Lee Lippincott. To see the model in its full glory, you'll have to go to Sproul Observatory just outside Philadelphia. The center of the sphere is at our position. The radius, the outside of the sphere, is 17 light years. We've taken quite a step up in size. Within this region, all stars more massive than about a tenth that of the mass of the sun are known. Less massive stars are dreadfully underluminous, very hard to spot. Finding them is still work in progress. I find it somehow strangely comforting to know, though, that all of the stars within this region are mapped out. That's where they are. Those are our star friends. There are 60 of them. I find it obscurely comforting also to notice that there are only 4 of them more massive than the sun. There are more massive stars. They tend not to be found, though, in our neighborhood, but rather near the places where stars form, in gas clouds such as this. A magnificent image coming from the Space Telescope here shown. Once Space Telescope got its spectacles, it is working at design specifications, producing magnificent measurements and simply stunning images of gas clouds lit, you see fortunately here, from behind by massive stars that burn very quickly and explode, leaving behind the products of nuclear burning, which is to say heavy elements that pollute the clouds, make them filled with dust, and so make these clouds look dark. Let us now look at the sky in a still larger scale. Oh, no, and let's remember that when a massive star exhausts its supply of nuclear fuel, it tends to explode. Here's the exploded remnant, seen in the radio, of Tycho Brahe's supernova. So let us look on a larger scale, and let us remember that if you go to a dark site high up, away from city lights, clear sky, you will see a band of light running across the sky. It's understood what the band of light is. It's simply a lot of stars blending together. Notice the dark rifts, not the absence of stars, but rather the presence of that obscuring dust. Here is a photograph of some people of whom I'll be making comments. I draw your attention to Arthur Stanley Eddington, lower left. Later on, I'll be talking about Professor Dr. William de Sitter, upper right, and Albert Einstein, of course, upper left. In the days of the end of the First World War, Eddington completed a book. Whoops. Wait. Where is the book? I remember. The book is over here. Entitled, Stellar Movements and the Structure of the Universe. Here is Eddington's universe. It's that Milky Way that you saw. Notice that the Milky Way is a band of light running across the sky. Eddington interpreted this as a disk of stars, shaped rather like a platter. With us rather close to the center, that was natural to him because that disk of Milky Way light is about uniform running around the sky. At the time, it wasn't recognized that the dust is there in great abundance and blocks our view along the plane of this disk of stars, so that we're not really at the center of the system. Instead, through this magnificent image, the COBE Satellite, of which I'll also be speaking more, we have this image at wavelengths slightly larger than are visible to our eye, and at wavelengths such that the dust is a lot less obscuring. We now see that we are on the distant outskirts of this shining city on the hill. But yet, the basic picture remains as Eddington had deduced it. We live in an island universe. This island universe, we have seen, contains gas clouds that create stars, that create the heavy elements out of which you and I are made. The heavy elements spewed into space, go into new stars, but of course always in the process there's loss, mass is left behind in stellar remnants, and eventually our galaxy, in about another third of its present age, is going to run out of gas, going to fade away. Galaxies are not forever. A message we should bear in mind as I proceed. Let us next recall that we're not alone in our island universe. Down below, another image of the Milky Way, of our galaxy. You see the glow of starlight. You see the dark rifts due to obscuring dust clouds. Up above it, you see another island universe of the same sort that happens to be seen again edge on. Notice the great similarity, the rifts of dust covering a smooth sheet of stars. Here's yet another of these spiral galaxies, this one seen close to face on, beautiful spiral pattern. Galaxies come in several varieties. Here's another galaxy of stars. Forward. Shall I press reverse? Hello? Up. What did I do? I'll let you people... Nope. May we back up two? Up, up, up. Now we go forward one. Again, you see a disk of dust and a faint glow of stars along the disk and a bulge of older stars. Shall I try to advance to the next one? And here, a galaxy with a bulge, no disk. Looks as simple as could be, doesn't it? It's fascinating, though, that if you look at this with great magnification, you'll see in the center a bright spot. This is a negative, so where it's dark, the image is really bright. A bright spot in the center of the galaxy and a jet of light running off to the side. What's happening here, I think, could be roughly compared to what happens if in the morning you're brushing your teeth and in your exuberance for the day to come, you squeeze too hard on the toothpaste tube. A jet squirts out. Here is an explosion in the center of this galaxy. It's thought due to the tremendous gravity that it can accumulate in a mass concentration very close to the center that has squeezed out a jet of material, to which I again plan to return. Now we have these galaxies. The galaxies themselves are spread around in space in a pattern that holds much fascination for us. Here is a cluster of galaxies called the Coma Cluster because it's in that part of the sky known as the Coma constellation. Each of these dots represents a galaxy. What you're seeing, I trust, reminds you of that diskless galaxy I showed you earlier, the one with the jet at the center. No jet here, actually, but a structure very similar to that galaxy. It is a galaxy of galaxies. We've moved rather far out in scale. This thing is maybe 10 million light years across. It is part of the structure of our physical universe. Here's an image showing the distribution across the sky of the nearest 1 million galaxies. It's again a negative. I wonder if for this slide we could turn off the... Yeah, that's great. It's a negative. Where you see dark, it is light. There are lots of galaxies. Where you see light, there are no galaxies. It's 100 degrees across, up normal to the plane of our galaxy, where the view is pretty clear. In the middle, the black spot, remember dark means lots of galaxies, is the cluster that is here illustrated. You see lots of other clusters here and there around. Because this image is so important to me, I would like to show you a photograph of the person responsible for making it. Donald Shane, he's the one on the left, is one of my heroes. In the decade following the Second World War, from about the late 50s to the late 60s, he and an associate, Carl Wertenen, at the Lick Observatory in California, spent those 10 years counting the brightest 1 million galaxies by hand with a traveling microscope. I had the pleasure of showing Donald this map, which was made with the help of these people, then graduate students, Jim Fry, Ray Siniera, and Michael Seldner, going toward the right. You can see Donald is a little uncertain what to make of these bright young guys, but he's getting along all right. And I had the pleasure of asking Donald, so is this the way you expected it would look? And he laughed and said, of course not. I was looking at this one galaxy at a time. Here, it kind of moves me to reflect, whoops, there it is. On the top shelf in my office is the pile of data sheets he accumulated after 10 years. Ask yourself, before high-speed computers, what do you do with 1 million numbers? Donald did a lot, in fact, but he really could not do more than skim the surface until we had high-speed computers that would give us this image. Now, I'm sorry to be flipping back and forth. I should be using that one, is what I'm now remembering. I had a plan at one time, and here it is. Let me draw your attention to another fact, that this side of the universe is starting to look a lot like that side. You notice I showed you here a galaxy of galaxies, but I'm not showing you galaxies of galaxies of galaxies, if you see what I mean. This part is starting to look an awful lot like that part. I offer another set of sky maps to illustrate this point. These galaxies were chosen because they are bright at very long wavelengths, detectable by an astronomical satellite, and so the search across the full sky is not much affected by the obscuring dust in our galaxy. This is the whole sky stretched out in equal areas so that if the galaxies were smoothly distributed, the dots would be uniformly distributed across this field. And they're not, of course. You see a great clump up here, a smaller clump down here. Let us now consider the experiment of asking where are the galaxies that are from the limit of this distribution to twice that distance. How does it look? Looks like this. Let's do the experiment again. Let's look at all galaxies that are from the limit of this case to twice that distance. We see this. I draw your attention to the difference. Here, lots of structure. Here, structure to be sure. Oh, I should have remembered to notice the obscuring dust in our galaxy does cause confusion along this plane. And there are a few strips where the satellite was unable to observe because it ran out of cooling helium. For the rest, notice what a uniform distribution this is. As we go to larger scales, we've stopped seeing new levels of structure. This is important enough to me that I'd like to show you some photographs of the people who have made this map for me. This shows the astronomers Sandra Faber and Mark Davis at an astronomical conference. Mark Davis was a graduate student at Princeton University, did a lot of work with me. Here, lower right, is Mark Davis's graduate student, Michael Strauss. Here are people at the Princeton Institute for Advanced Study, where Michael went after completing his studies at Berkeley University. Here are some of the best and the brightest of the next generation of astronomers. Someday they'll be rich and famous, and this photograph is going to be worth a bundle. To come back to the main point, notice how structure is starting to be washed out. Let's go on and look at still deeper samples of our physical universe. We can do that by radio galaxies. Remember I mentioned the jet in that galaxy without a disk. Sometimes these jets are so violent that material is expelled quite from the galaxy. This material contains very energetic electrons that make radio emission. This is a radio map. Until we had radio telescopes, no one could see this. When we see it, and I should remember to stress that the galaxy itself is that little blob in the center, we see this wonderful image that somehow moves us. It's an image no one has ever seen before. It's part of our physical world, and isn't it elegant? Not only is it elegant, it's very prominent. These things can be seen a long way away. And because they're rare, this is a rare event, when you map out the distribution across the sky of the nearest 30,000 or so, you get a very large-scale picture of what our universe looks like. Here is the picture, made by Jim Condon, working with Gregory at the University of British Columbia, Condon at the National Radio Astronomical Observatory based in Charlottesville, Virginia. This shows one half of the sky. The hole in the center, you must understand, is instrumental. That's not absence of galaxies at this point. The Milky Way, our galaxy, is running in this particular projection along this line. You should ignore, for example, the fact that there's a bright source there that confused the telescope in the immediate vicinity. The sun got in the way along here. Elsewhere, what do you see? Nothing. It's quite a change from what we were seeing on smaller scales. This is, oh, and I should remember to show you the telescope that made this magnificent image. Well, in fact, I think I have a, yes. It was built as a temporary structure, and of course, you know what happens to temporary structures that are useful. They keep being used until just as this map was being completed, it gave, I guess you could say, the mechanical equivalent of a deep sigh and fell down. It's all right. A new telescope is being built at this site that will be bigger and better when completed. Now, what have we got? We have a remarkable result. We are so used to knowing that there are layers of complexity in the world. There are atoms that have substructure, atomic nuclei. The atomic nuclei have substructure, going down to quarks. The atoms can be organized into molecules. It can be organized into human flesh. It can be organized into people or into societies onto this Earth. The Earth concentrated in a galaxy that's part of a concentration of galaxies. It's on the outskirts of a cluster of galaxies, layer upon layer of structure. But as we probe to larger scales, we run out of structure. And that, of course, is why we can pretend to have a theory of the universe as a whole, because we've reached the end of the level of structure so far as it can be observed. This remarkable concept, in fact, even more remarkably, was deduced ahead of time from pure thought by Albert Einstein. He felt, for reasons that I've never understood, that the only logical universe is one that would be uniform in the large-scale average, so that it would look the same in the large-scale average in every direction. He had no idea what a galaxy is, much less how the galaxies are distributed, yet somehow he hit upon the right idea. He proposed that a sensible universe would be uniform in the large-scale average. He ran into a problem. He had a theory of gravity, general relativity theory. This theory of gravity, with that assumption of a homogeneous universe, required a terrible messing up of his theory to be self-consistent. It didn't occur to him, so far as I can ever make out, to reflect that the universe he wanted to build, which would be homogeneous but static, a universe that would be forever, would be useless, because galaxies cannot be forever. It fell to the person on the right, the Abbé Georges Lemaitre, to bring together astronomical clues that perhaps our universe is not forever, but maybe instead expanding, with Einstein's general relativity theory, to give us the theory we now accept, the expanding universe. I offer you an example of this expanding universe theory. In this, a caricature of Professor Dr. Willem de Sitter, who we met earlier, being interviewed in a Dutch newspaper just after Lemaitre's work came to the attention of the international community. And Lemaitre offered this example of an expanding universe that still holds as an excellent way to visualize it. Pretend that instead of being able to move around in 3 dimensions, we can only move around in 2, on the surface of a sheet. Imagine that this surface of the world we live in, 2 dimensions, where ants crawling on a surface, is a sphere, in fact, the section of a balloon. You must ignore that little part, of course. Here are the galaxies painted on the balloon, except I should be careful to say they're not painted on, they're stuck on. We're going to blow up the balloon. Galaxies don't expand. The Earth doesn't expand. But the distance between the galaxies increases. And you'll notice that wherever you sit, you'll look around you and you'll see galaxies moving away from you. Notice also the elegant construction. If you walk in one straight direction, you'll come back to where you started from. We've created a universe that's homogeneous, yet it has no edge. Now imagine, if you would, that we take this expanding balloon in 2 dimensions, we make a balloon of 3 dimensions expanding into some other mythical 4th dimension. Don't bother about the extra dimension. Here is our expanding universe. Now, it fascinates me to reflect that Eddington and Lemaitre had rather different opinions on a key issue. Eddington was remarkably receptive to new ideas, and in fact, he was the one who saw the importance of Einstein's general relativity theory, the theory of gravity that requires this evolution, and organized the first tests. And he also embraced Lemaitre's idea of an expanding universe as a way to understand astronomical observations. But he was repelled at the thought that if the universe is expanding, it had a definite beginning. Here is the short comment. Professor Sir Arthur Eddington states that philosophically the notion of a beginning of the present state of nature is repugnant to him. On the other hand, Lemaitre celebrates this, saying, if the universe had a beginning, think of the new physics we stand to learn in understanding what that remarkable statement means. You can't help but notice that Lemaitre was religious. So was Eddington, a member of the Society of Friends, the Society of Friends of Truth, a Quaker. But on points, I think you have to give it to Lemaitre as being the more religious of the two. And I had often idly wondered, what interaction did Lemaitre's religion have to his eagerness to think of a universe that had a beginning in what we now sometimes colloquially call the Big Bang? I can't tell you the answer, of course, but I can show you some quotes that charm me. Notice the statement, after all, a Christian does not act differently from any non-believer as far as walking or running or swimming is concerned. Now, I think in this day and age, we would have to call Professor Georges Lemaitre to task here. I'm sure Muslims swim in a similar way to Jews or atheists or agnostics or the rest of us who are confused. The basic point, though, is clear. If you are going to indulge in swimming, you'd better do it the way everyone does. You might do it better or worse than others, but there's only one way to swim. You hold your breath and flail your arms. If you're going to do science, there's only one way to do it, the way everyone does it. I'm charmed by his comment at the bottom of the page. It never had to be a question of reducing the supreme being to the rank of a scientific hypothesis. So, let us turn to a remark, a quote from Lemaitre on the bottom of this page. I might remark that he is another of my heroes. In the early 1930s, he was the one, I believe, who best understood this notion of an expanding universe, who saw the sort of tests that would be required to establish it as really scientifically acceptable. And in particular, he stressed, well, notice the quote, the evolution of the world can be compared to a display of fireworks that has just ended. Some few red wisps, ashes and smoke. Standing on a well-chilled cinder, we see the slow fadings of the suns, and we try to recall the vanished brilliance of the origin of the worlds. Lemaitre stressed that if the universe really did evolve from a state very different from what it is now, then surely nature will have left behind fossil evidence of that very early time. He proposed that the cosmic rays might be the fossil evidence. The fossil that I'm now going to turn to discussing is instead the thermal background radiation that Craig mentioned. As part of the Second World War effort, there was a lot of work done on nuclear physics that after the war led George Gamow to think that if the universe had expanded from a dense, hot state, then much the same thermonuclear reactions that go into an atomic bomb might have happened in the early dense states of the universe and have produced the heavy elements. Ralph Alpher's thesis with with Gamov on this subject was the occasion of one of Herblock's cartoons. Some of you might remember when these were shown and chilled us to the bones. I believe historically this is the first occasion on which Herblock used his new symbol for the hydrogen bomb as opposed to a fission bomb. Scientist says world was created in 5 minutes. That's the Big Bang, the hot start to our early universe that would produce heavy elements. To make this story fly, the universe had to be hot, so thermonuclear reactions would burn material. Material that's hot makes radiation. You tell me the temperature, I'll tell you how much radiation you make at each wavelength. Ask yourself now the question, what happens to this radiation as the universe expands? Well, it doesn't go away, does it? There isn't any edge to the universe, no place for that radiation to go. Instead, it gets adiabatically decompressed, much as the gas in your cylinder of your car cools off as it does work in expanding, in pushing on the cylinder. This radiation would still be present. If this whole story made any sense, this thermal radiation produced when the universe was hot and dense ought still to be around, if this story is correct. Here is a photograph of Ray Weiss, who I will mention a bit later on and on my lecture on Thursday, pointing to another temporary structure, a building at the back end. You can tell it's not the front end, the back end of MIT, pointing to the rooftop. On that rooftop, during the Second World War, Bob Dicke, in this dark suit to the right, is holding a shaggy dog, so-called, a piece of felt that is black, against this device, which you can see now in a very faded exposure. He made, during the Second World War, as part of the radar effort, called a microwave radiometer, a device made to detect thermal emission, this radiation given off by all bodies that are above absolute zero. Here is an example of what he could do with that radiometer. During the Second World War, Cambridge was an industrial city, a smokestack city. It had factories. The factories had smokestacks, and the smokestacks were belching smoke and were warm. Here is the result of his scanning this radiometer along the horizon at different angles from the horizon, showing that whenever the radiometer looked over one of these hot chimneys, it gave a deflection. It was sensitive to thermal radiation. Bob used this device as important aspects of war research. For example, during the war, there was an enormous pressure to get radar at ever shorter wavelengths because it gives much better resolution. The effort pushed from meter wavelengths at the start of the war to centimeter wavelengths at the end, and beyond to millimeter wavelengths, where the effort failed. Unexpected to the people developing these things, the atmosphere is rather opaque at shorter wavelengths than a centimeter. It was Bob's radiometer that cleared that confusion up. He also used this radiometer during the war for a little science. In particular, in a piece published after the war was ended, he pointed this radiometer first at the moon and measured its temperature. It's around 300 degrees, same as the Earth. He then pointed the radiometer at dead empty space and concluded, as is shown here somewhere, very little, less than 20 degrees above absolute zero, radiation from cosmic matter at radiometer wavelengths. Now, some 2 decades after that, it occurred to Bob Dicke that if the universe really did expand from a dense state, and if it were warm when it was dense, there would be this radiation left over, and it might be a good idea to attempt to detect this radiation. The machine you would use to detect this radiation is nothing but this Dicke radiometer. He persuaded Bob Dicke is on the left. In the middle, Jer Yu, my first graduate student. On the right, David Wilkinson. He persuaded David Wilkinson and his colleague Peter Roll. Peter Roll is just hidden in behind coyly. You see he's got a checkered shirt. This could be focused a bit. And David Wilkinson, you see looking very intelligent and holding a screwdriver, staring at a Dicke radiometer, built for the purpose of looking for this radiation. News of this experiment reached Holmdel Laboratories of Bell Labs, just 30 or 40 miles up the road from Princeton University, where the telescope in the back had been used in the first of these echo communications experiments, in which, now an everyday occurrence, a signal is sent from Earth to a satellite, bounced back down to another part of the Earth, a very reliable and efficient communication scheme. The engineers who built this first prototype were disconcerted to find that they were getting a little more noise from their instrument than expected from its properties. After the experiments with communication, these two guys, Arno Penzias on the right, Bob Wilson on the left, were given leave to use this telescope for astronomy, but their very sensible bosses said, look, before you do any astronomy, you explain to us that you understand your instrument by showing us where that extra noise came from. They put a Dicke radiometer into this thing, tuned it up to the best of their abilities, were going crazy, trying to understand where this noise was coming from, until word reached them of the experiment at Princeton, and they realized they might have it. It's funny how human nature operates. I remember Arno Penzias saying to me, his first reaction was, well, at last we can forget about this crazy noise and go on to do some science. Now, if this radiation were indeed left over from the Big Bang, here would be the prediction. This radiometer works is sensitive to radiation with a wavelength of 7 centimeters. Is that about 7 centimeters? Close enough. They measured a definite amount of radiation at that wavelength, isotropic across the sky as you would expect if this is radiation filling space uniformly. Having measured the intensity of the radiation at one wavelength, you know the temperature, because after all, black-body radiation is defined by one parameter, the temperature. Knowing the temperature, you can predict what the intensity ought to be at every other wavelength. You can't cover all wavelengths, of course. At very long wavelengths, there are those radio galaxies I mentioned to you that would get in the way. At very short wavelengths, emission from stars and dust in our galaxy would get in the way. In between, there is a window where you ought to see this very smooth shape, if that's the way it is. As you can imagine, this led off to a heated race to try to make more measurements to see whether or not they followed this definite prediction. Fortunately, the experiment by Peter Roll and David Wilkinson was at 3 centimeters wavelength, about there. It came in just a few months later and gave the first bit of encouragement that this prediction might be on the right track. This part of the curve was mapped out pretty quickly and did agree with the prediction, because one really was using standard equipment in use in a slightly different way, and one was discovering, of course, a new phenomenon. But about here, the atmosphere just gets too opaque to do the experiments. You had to get above the atmosphere to measure the spectrum over the curve. There then became a scientific race to get above the atmosphere, measure the spectrum over the curve, see if it agrees with this prediction. Of course, scientific races of this sort are rather like watching paint dry. They don't happen overnight. Well, paint dries overnight, I suppose. The race took about 2.5 decades. Here is a team assembled for the purpose of building the COBE Satellite that I showed you a picture of earlier, for the purpose of measuring the intensity of the radiation over the peak of this predicted curve to see whether or not that's the way it really is. I pointed out to you Ray Weiss. I'll have some more to say about him on Thursday. Dave Wilkinson. John Mather just has a book out on his experiences over a decade and a half of effort to build this satellite. He has got to be counted as another of the heroes in this game. He took on this project shortly after graduate school. For a decade and more, he had no publications, no advancement in his career. He put it all on the line for this one satellite. Now, you know that what is it, one satellite in 30 blows up on the launch pad. And if it had, there would have been his career, or at least a decade and a half of it. Yet he stuck with it. In his book, I was just exhausted by the detailed accounting of crisis after crisis solved. Nancy Bogus appears very prominently as the one who held this thing together and kept the funding flowing despite competition from other very worthy satellites. Before I show you the results of that experiment, I must show you a photograph of the competing team. This, a measurement to be done from a rocket rather than a satellite on a much more modest budget by Herb Gush and Associates at the University of British Columbia in Vancouver, just up the road. Here is Herb with the instrument package, exhausting what he went through. One successful flight released the package from the rocket, drifted away from it to get rid of away from the contaminating gases from the rocket. The rocket then reignited, rushed forward, passed the instrument package, sprayed it with noxious fumes, knocked it out. Oh. Here are the other two people on the final successful flight, Mark Halpern and Ed Wishnow. I just can't resist it. Because these people did something great, we are entitled to let our sense of humor roam. And I'm entitled to ask you, just looking at this image, knowing nothing about what they did, knowing only that you have this image, would you ask these people, would you hire them to paint your front porch? Well, you see, we've just learned something. You shouldn't make such judgments, should you? Because these people did do something absolutely stunning. A remarkable coincidence that each of these experiments took over a decade to bring to fruition. Yet they were completed within 2 months of each other. And that was important because you had an independent check. You had to believe the result. Here was the result that Dave Wilkinson first showed me. The COBE satellite was launched, and of course, after you've gotten the first data, you sit on it a while. You ask, have I made some horrible blunder? And while you're sitting on these data, you have your good friends. And at some point, you have to decide, I have to tell them, I have to tell people sometime what the result of this measurement was. So for a couple of days, I was entertained by the fact that David Wilkinson was walking around smiling, from which I knew it had to be about like this, a wonderful success, because if it were against the idea of a hot Big Bang, surely he would have been frowning, wondering if somehow they'd missed. Then there was a day when he drew me aside, and rather in the fashion of being shown filthy photographs, he showed me this, swearing me to absolute secrecy. But it's stunning. These dots are not, they're the measurement. The line is the theory. It's stunning. Here is another version of the same data on a very different scale, logarithmic. So there are lots of decades of wavelength, lots of decades of intensity. The thin line now is the theory. The thick line is the measurement, UBC and COBE. The uncertainties in this measurement, and I should mention that a few ground-based and rocket points and a few other measurements are interspersed here and about. This is the range covered by those experiments in wavelength. The uncertainty in the measurement over this peak is small compared to the thickness of that line. At longer wavelengths, here are measurements from the ground. Notice a stunning agreement of theory and experiment. Here, I think it's not an exaggeration to say, is manifest evidence that the universe expanded from a dense state. Manifest, as I would say, as the evidence that dinosaurs walked this earth from the fact that one sees their bones lying around and one sees their footprints frozen into rock. Because one can't imagine how radiation with this very characteristic shape could have formed in the universe as it is now. To form this radiation, the universe has got to relax to statistical equilibrium. The universe now is quite transparent. We could see those radio galaxies at great distance. This radiation was not made in the universe as it is now. Our universe indeed is not forever. This radiation shows us that it went through a hot, dense phase and has expanded away from it. I hope you get the connection. In the early days of this century, Einstein inventing a theory of gravity and inventing on philosophical grounds, I suppose, the notion that the universe is homogeneous. Lemaitre taking that idea of general relativity theory with Einstein's idea of homogeneity and deducing that the universe ought to be either expanding or contracting. What's consistent with the astronomical evidence is the universe expanding from a dense state, giving the galaxies a finite lifetime, around 10,000 million years. Galaxies are not forever, consistent with the fact that our universe, as we see it, is not forever. I think I'll now conclude with the 10 most commonly asked questions about this stunning conclusion that our universe is not forever. First question, where did this Big Bang occur? Can you point to the place in the sky? Now wait, you weren't paying attention. I showed you image after image of the distribution of matter, showing you that it's the same in that part of the sky as in that part. There wasn't a localized explosion. That's not the picture at all. The universe everywhere is expanding. There's no sight. What was our universe like before this Big Bang? Well, I don't know. That's not part of the theory. I'm describing a universe that evolved from a dense state and expanded and cooled. Of course, one attempts to make theories for what the universe was like before it was expanding. Visiting this university and making available to an eager public a book, The Inflationary Universe, is Alan Guth, who was one of the pioneers in discovering physics that might tell us what the universe was doing before it was expanding. Wonderful ideas being explored, but after they're explored, we'll be back to the same old question, right? So what was the universe like before it was inflating? And he'll have to say, well, I don't know. I'm working on it. So will our universe continue expanding forever? Is that all there is? Expands, drifts off to infinitely low density, that's it? That's all? Maybe our universe is massive enough that gravity can slow and stop the expansion, after which the universe would collapse back to a big crunch. That would be fun. And maybe in the big crunch it's a bounce, and our universe starts expanding again. Well, that could be. I don't know. But I certainly don't know how you'll ever, I don't know with the present evidence whether you'll ever be able to show that this is what happened. How can you claim to have a complete theory when you cannot even say what happened before the Big Bang? Because I'm trying to account for the universe that we see it now and as it was back in time for a limited extrapolation. Why do you keep avoiding the name Big Bang? Because I think it's a terribly misleading name. There's nothing about an explosion in all this. Bang, to me, connotes localized. That's not the way it is, isn't that right? The universe is expanding forever. And what caused that expansion is still part of the research of science. It's not part of that we've established. What I think we've established is that the universe has expanded from a dense state to the present. If you're so smart, why aren't you rich? Well, try to bear in mind that because this is a topic in research, there are inevitably open questions. It's easy for you to ask me questions that I can't answer. Prominent among them, as I will discuss next time, is the simple question, so what is our universe made of? Doesn't seem to be the ordinary material of which you and I are made. So what's the nature of this material? I don't know. It's a big hole in the theory, but that's what we have to learn to live with. What I'm trying to argue, to suggest, is that although I'm not rich, we are at least making progress, and we have nailed together a few planks in what seems to be a pretty sturdy picture for what our universe is like now on very large scales. Thank you.
I'd like to answer some questions. Sure.